So let's look a bit more at the shared page cache. This is another one of the components in the system. The shared page cache is a large chunk of memory that holds shared data. Counters, again, there's counters available, so multiple sessions can see a number that's just simply stored in the shared page cache. Statistics, each process writes information about itself into the shared page cache. And then, of course, repository pages. We read from the disk into shared memory. That's where we get the data. Counters, an integer available to any gem that's on this host that's connected to this shared page cache. 32-bit number. All operations here are atomic outside of a transaction. So you can increment a counter in one virtual machine, in one gem, and look at the value and it'll be immediately visible in another. However, since these are stored only in the shared page cache, they're not persistent. So each time the system starts, they're initialized to 0, and then it's simply up to the sessions to look at them. Okay, we also store statistics in the shared page cache. Each process on the host attaches to the shared page cache and records statistics in real time. Separate process attaches to the shared page cache and reads the statistics for everything else, writes it to a file, and then that's used to debug, to do performance tuning. So statistics are very interesting. Then the pages themselves, the actual pages from the extent. Each page represents part of the repository and is in RAM. So the shared page cache is where pages are shared, that are cached, pages that are cached in memory are shared among multiple processes. So permits objects to be read from and written to memory rather than the disk. And the shared page cache is made up of frames that hold a page. So the page is the space on the extent and the objects in it, and the frame is the place in the shared page cache where the page is currently held. So a page could be held in different places at different times, but once it's in, then everyone can see that page in memory. Now, when we want to load something into the shared page cache, we need to have a place to put it. So again, there's frames in the shared page cache, but we need to find a place to put the page that we're reading. So first is a free frame list. The free frame list is a list of cache frames that are not in use, that are free. It's maintained by the shared page cache monitor. So there's a process that monitors the shared page cache, keeps track of the free frames. You remove a frame from the list when you need one. So if you ask for a frame in which you're going to put a page, you can get it from the list and it gets removed. And finding free frames from this list is very quick. You just simply go to the list, pull something off, and there you have a new frame. But if the system gets constrained, and if this list gets short, if we ran out of lists, ran out of entries in this list, then we have to scan. You have to go through the entire shared page cache looking for an open space. And it takes much longer to scan. Now it's in memory, so we're not going to disk, but it's still examining each frame to see if there's space, to see if it's free. So there's a priority of when this list gets short, then use of this list is restricted to special processes. So if there's less than a certain number of free frames, then certain processes might have to scan. And that's slower. Before you can write something, before you can use a frame that's in use, before you can replace a frame that's in use, you have to write it out. If objects on that page have been modified or are dirty, then that page needs to be written to the extent before we can use that frame, before we can use the space in memory. So AIO, asynchronous I/O, asynchronous input-output. These are processes that simply scan the shared page cache. Every time they find a dirty page, they write it to the disk. And so this keeps the disk busy, but it keeps the shared page cache clean. And that way, other processes don't have to wait for disk. These processes are waiting for disk, but that's their job. So the asynchronous disk I/O, it's a separate process, scans the shared page cache. Committed pages that are dirty need to be written to the disk. Dirty pages are written out to an extent, and they're done in small groups as system load allows. And then every now and then we have what's called a checkpoint when everything gets flushed out to the disk, just so that as of that point, we're clean. We want to be able to find space in the shared page cache. Scanning to look for space can take time. So you can configure a free frame server. That is a process whose job is simply continually scan the shared page cache, looking for empty slots, empty frames. If there's a frame, put that frame into the free frame list. Make sure that it's in the free frame list. If it's in the free frame list, then someone can get it without scanning. So this is kind of a way of parallelizing the operation. Someone's job is just to scan the shared page cache, adding it to the free frame list. They can't be dirty. That's the job of the page server. They can't be in use. If a gem is attached to a page, then we can't free it. And then there's a complex algorithm to see how recently was it used. Because we want to write out we want to free slots that haven't been used for a while. So if the page hasn't been used for a while, then we can write it out. But if it has been used recently, then perhaps it'll be used again soon. The question is, why separate the AIO page server from the free frame page server? And the answer is that it could, in the sense that they're both looking at the shared page cache. But the AIO page server is spending most of its time waiting for the disk. And if it's waiting for the disk, then it's not scanning the shared page cache. And as long as these are actually separate processes that just happen to be looking through the same chunk of memory, we'd rather they be in parallel rather than in series. So particularly if you're on a CPU if you're on a computer that has multiple CPUs or multiple cores, multi-core machine, the free frame server is simply limited by how fast it can run. Whereas the page server is limited by disk. So having one process that's limited by disk separated from a process that's limited by CPU is reasonable. On the free version of GemStone, one of the limitations is that each process will limit itself to running on only one CPU. You can have a multi-CPU machine, but they'll all use CPU 0. And so it won't run in parallel in that case. Now, that tends not to be too big a limitation because in the free version we're limited to 4 gigabytes of data and 1 gigabyte of shared page cache. These are kind of performance optimizations for very large, very complex systems, but can be useful in certain situations, can be extra overhead in others.